Okay, let's start with a quick recap of what we saw last time. So last time we saw a first order system, and we computed its response when the input was a sinusoid. So we considered the first order system response, and the main result was the following. We had our first order system. I put here in the box how the system works. It's first order, so x dot is equal to ax plus bu, and y is of the form cx plus du, but we assume that du was equal to 0 just for simplicity, and you'll see that this is not a big assumption. We just need to add du to the output and repeat very similar computations. Actually, this is going to be in your first homework to analyze the case when d is not equal to 0. So far we have just considered a simpler case when d is equal to 0, and the idea was to put as an input something of the form with a sinusoidal form, cosine of omega t. Sorry, this is a u. U is cosine of omega t, and we computed our y of t. The main result was an explicit form for the expression of y when the input is equal to 0, and remember also the initial condition was equal to 0 as well. If the initial condition is not equal to 0, still we have the free response, so we'll need to add the free response to y of t. So y of t, the expression that we got for it was a cb divided by a square plus omega square exponential of at plus cb divided by the square root of a square plus omega square cosine of omega t plus v. So what we found is that the forced response is given by a transient term, transient if a is less than 0. If a is greater than 0, all this analysis still holds, the expression is still correct, but the exponential is going to dominate very quickly whatever you get from the cosine, because the other term, that is the steady state response, again if a is less than 0, whatever you have, if a is greater than 0, your this term that is multiplied by a cosine is bounded, so quickly the exponential will come to dominate the steady state. But if the system is bibostable, and if c and d are different from 0, then the fact that a is less than 0 makes the exponential term go to 0 pretty quickly, and so we are only left with this steady state response. The interesting part is that the steady state response has the same frequency of the sinusoidal input, and this is the first fact. So we have that the frequency omega of the steady state response is equal to the frequency omega of the input. Not only we have an amplitude that is given by cb divided by the square root of a square plus omega square, and we have a phase shift given by this phi, that is the arctan of omega divided by a. So this is what we saw the other time. What we are going to see now, let me just quickly save this. What we are going to see is we're going to verify that this expression is correct, and we are also going to draw the Bode plot of this first order system. So in order to verify this, we are going to use MATLAB. So we go here in MATLAB that I have already opened, and the first thing that I want to do is to check we are already in the directory where I keep all the MATLAB files of this course. So we had this first order system, that is this Simulink block here, that as you can see we just have the state x. We are going to compute, if we want we can compute y very quickly, but let's keep just this system. Let's just keep this Simulink system to compute x, and we'll compute y manually. So this is the block. You can see that a and b still need to be initialized. One thing that I want to check here is that everything is okay in the sense of parameters. So I want to put an amplitude that is equal to 1, and let me see the phase. So if I put the phase equal to 0, if we check here in the description of this function, it says that the output is a sine wave, so it's a sine. We did all our computations using a cosine, so what I want to do here is to choose as phase pi divided by 2. If I choose pi divided by 2, I have sine of omega t plus pi divided by 2, so this sine becomes a cosine. So with this phase shift, what I have is not actually a sine wave but a cosine wave. And what I want to put here is a frequency omega that is variable. I want to manipulate it from the workspace. So now my sine wave is going to give me a warning Q, because the frequency that needs to be expressed in radians per time, per second, still has to be specified. So this is our block, and just to be sure, let's check also the configuration parameters here. I'm using, you might have some, if you try to replicate what I'm doing now, you might get some slightly different results if you use a different solver. In this case I'm going for a variable step, and I'm considering ODE for 5, the Dorman-Prince solver. So I'm okay with these parameters here. The important thing is that the relative tolerance needs to be small enough, and this is definitely small enough. So having done this, I just need to, what I want to do now is to simulate the system. I'll compute manually what the output is. I just choose what C, the variable C, is going to be. Remember, D has to be equal to 0 so that we can, so that our formula makes sense. And so in order to do this, I'm going to the directory where I have all our MATLAB files, and I have already prepared a short script. So what we are going to do is to go through the script to see what the script does, so that we don't have, since I want to repeat this script for several values of the parameters, especially omega, I don't want to retype every time everything. So let's open this script that I have already prepared. It's a very simple script. Now let me do this. Now that you can read this clearly, we don't need this comment, but now I'll start commenting this while I'm going over the script with you. So let's write some comments. Always comment the code that you write. So as you can see in the first block, in the first 4 lines, I'm defining 4 scalars, a, b, c, and d. They're exactly the a, b, c, and d of our linear system. So these are the, I write here, parameters of the linear first order system. One thing that I'm going to change often is the frequency of the input, and this has to be in radians per second, so I'll add rad per seconds. Then here I'm computing the phase shift of the output, and then here I'm going to simulate the system. So you don't need to go into the Simulink interface and click run or Control T to simulate a system. You can do that from the command line, and if you're running a script like what I'm going to do now, that's actually much more convenient. So this simulate the first order Simulink model. And now we have the interesting part. As you can see, that's the main reason why I have already prepared a script in advance. I am predicting what y is going to be. So first let's compute y. So compute y of t from the simulated model. And y of t is going to be, after we simulate the Simulink model, as you can see, if we go in our Simulink interface, we have a variable t that is a standard array that is being exported into the workspace, and we have the state x. So if everything goes well during the simulation, we have a variable t, an array, and another array x. So what we are going to do is just to compute this in this very simple way. U is 0, but still, just because I want to be precise, I'm going to add this term du here. Cx would have been enough. So this is the y as it comes out from the model, because x comes out from the simulation. So what is predicted, if everything is correct, is that is the analytical solution of the response. So we are going to verify this, and now we do also the plot at the same time. We plot t and y. Not only, we hold on. Remember, hold on keeps the previous plot in the figure, and then we'll plot t versus the y predicted. And just to show that this is fine, we are going to plot that in red diamonds. So the solid line, the solid blue line, is going to be the simulated model that we assume is sort of the ground truth, if the simulation is correct, and predicted, or the analytically computed, is going to be plot as well. Okay, so this is our script. We are going to run it and see what happens. So we can, of course, I'll post this script in the class website. So the script is called firstResponse.m. So if I run first response, after a few seconds, I hope, if everything is correct, I should get the result here. Okay, this is the plot, and as you can see we have a solid line. We have a bit of a transient here, but as we can see, this is, I'd say, as good as it can be. We can actually zoom in and check if the computation that we have done is pretty much on the spot. So what we had analytically computed actually matches the result of the simulation. So we can say that that formula is most likely correct. Since I have a script, pretty much we are paying no price if we we are paying no price. Let me run it again with exactly the same parameters, because I forgot to have you notice what the amplitude is. If you see, the amplitude is around 0.7 something in terms of amplitude once we reach the steady state. Let's try to increase omega and let's see what the amplitude becomes. So if we just change omega, and from 1 we make it 10, and we clear the workspace and we repeat the same script, now we get something that seems a little busier, but let's see if we can zoom in. It's a little busier for a simple reason. The frequency of the input now is 10 times. So in the same time when we had just 1 oscillation, now we have 10 oscillations. But as you can see, again, the computation that we had is correct. And the higher frequency leads us to some oscillations that are way smaller. Now the oscillation amplitude, as we can see, if I zoom out, is between minus 0.1 and 0.1, so the amplitude is 0.1, roughly speaking. So as we can see, this amplitude is way smaller, and that's precisely what was implied by all our computations. Now what I want you to see is, in principle, we could repeat this analysis for many values of omega, somehow to find a way to compute the amplitude and start plotting our Bode plot, or otherwise we have our expression for the amplitude gain. We'd like to plot. So after verifying that this is our amplitude gain, CB divided by the square root of a square plus omega square, after verifying this and after computing our phase, we can use these expressions to draw the Bode plot. And I just want you to remember what the Bode plot is. The Bode plot is actually two plots, because we are both plotting the amplitude gain and also the phase shift. So what we do typically is this. Well, it's not necessarily less than 1. We have our omega. Remember that omega has to be in a logarithmic scale, and also we have another axis for omega in logarithmic scales, so that we can plot the phase shift. So here we put the absolute value of the amplitude gain, and here we put the phase shift. So we write it in this way. let me complete this sentence here. The steady state responds to the same frequency of the sinusoidal input. So I'd say, I write here y steady state of t has a certain amplitude cosine of omega t plus pi. I just want you to stress one thing. So far, let's assume that C and B have the same sign, so that the term CB is positive, so that this quantity here is the gain. If this quantity here is the gain G has always to be positive. So if C times B is negative, it's the only thing that can make this term negative, then we'll have to modify, we can make it positive by readjusting the phase here. So don't worry about that. So far, let's assume that C and B are positive, and that's what we are going to do. We are going simply to plot for different values of omega what the amplitude is going to be. We can do this just using these expressions, but I just want to draw you what this is going to look like qualitatively. So it's going to be something of this kind, depending on the specific values that you have for omega, A, B, C. But you have that this tends to follow this kind of behavior, at least in logarithmic scale. We are going to verify that using MATLAB. And then we'll see what the phase shift looks like, but it's just going to be the arctan of omega divided by A. Remember that A is negative because we need a form of stability for our system, and so it's going to be something that it's just since everything is going on a logarithmic scale, we are simply going to see somehow a stretched form of the arctan. Okay, so I just want you to know. I just want you to see what the plot looks like. Just if we are just going to write this in this way, what this is going to look like is the following. When omega is very close to 0, this is going to be a quantity that the arctan of 0 is going 0, slightly negative because A, we are assuming that A is negative, so it's going to be like this. And then at a certain point, when omega is very, very, very large, then this arctan is going to be the arctan of minus infinity. Remember that A is negative, so when omega goes to plus infinity, omega divided by A goes to minus infinity, so it's going to be minus pi divided by half. So when omega goes to infinity, this is going to be minus pi divided by half, and so this is pretty much going to be the behavior depending on the values that you have of omega and so on. So this is, if we use this expressions, we can draw these plots analytically in a very, very precise way. I want to show you in MATLAB what happens, and then we'll see some other ways where that we can use to draw these plots, not in a precise way, but just in an approximate way. And these sort of asymptotic plots, as they're called, they're going to become very important because in some cases it's not that easy to have an expression so nice for the amplitude gain and for the phase shift. So if we have this asymptotic plots for simple systems, then we can put them together and draw asymptotic plots for more complex systems, and that's one of the techniques that we are going to see later on about drawing Bode plots. So far I just want to draw your attention on the fact that for first order systems we have these expressions. This is the Bode plot. Conceptually tells you if you are injecting a sinusoidal input into your system, you have an amplification or attenuation of the amplitude, and at the same time you're going to have a phase shift, and both these quantities depend on the specific frequency that your input has. Having said that, let's see how do we plot plot a Bode plot in MATLAB. In MATLAB it's actually quite simple. First we need to define a system, and the way to define a system is using the ss state space command. So the ss command, if we check the help, tells us wants simply the matrices A, B, C, and D. In our case, they're just scalars, small a, small b, small c, and small d, and creates a variable that is nothing but an object, a structure variable, representing this expression here, this system, x dot equal to ax plus bu, and y equal to cx plus du. There is an additional parameter that you can give. The system can be continuous time or discrete time. In this class we are always using continuous time, so there is no reason to give any sampling time to the system for the discrete time. So in this class we are only dealing with a continuous time, so don't worry about that. So we are going to create, using this function here, ss, a system. I call my system S, and I'm giving A, B, C, and D that come from the script, the way I have initialized them in the script. And so I define my system in this way. So now I have this object S, and this object S can be manipulated with many functions in MATLAB designed specifically to manipulate systems. One of these functions, you can guess, is Bode. So if you type Bode S, that's what we are going to get in a second. This is the Bode diagram, and as I told you before, for the magnitude that we have here, we have this kind of behavior. So I want to stress a couple of things. Observe that it is specified by MATLAB that the magnitude is measured in dB. And as you can see here, on the axis that we have here, the frequency is in a logarithmic scale. As you can see here, we have 10 to the power of 0, that means omega equal to 1. Here we have omega equal to 10 to the power of 1. And here we have omega equal to 100. And we have omega equal to 1/10, omega equal to 1 divided by 100, and so on. Omega equal to 0, when you take the logarithm of 0, you get, of course, it's not defined, so when omega goes to 0 plus, you get minus infinity. So it means that on this scale, on the logarithmic scale, you always have only positive omegas, and when omega goes to 0, in this scale, when omega goes to 0 plus, actually you see in this scale going towards minus infinity all the way to the left, because the logarithm of 0 plus is minus infinity. Instead, when omega goes to infinity, the logarithm of infinity is infinity, so when the omega equal to infinity is still on the right end, the extreme right end of this scale. So this is how you plot your Bode diagram in MATLAB, now that we have nice computational tools to do this. What we are going to see later on, after introducing the Laplace transform and we consider a higher order systems, we'll see that Bode diagrams are not so easy to compute analytically. Of course, we can use numerical tools nowadays, but with asymptotic plots, we can still draw a Bode diagram, a good approximation of the Bode diagram, even for complex systems, in a very, very simple way. So let's say that we pause here, at least for this first segment of the class.